Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I would like to welcome you all here today to hear Wynn Burleson, whose last name I may be mispronouncing, but whatever, talk today. And I met him first at CSCW this fall, and we just had a really great and fun conversation. And I think there's lots of stuff that I'll talk about today that will be fun and interesting for folks to hear. So we'll keep this very interactive, I'm sure.
Great.
And he can tell you more about his bio, but you probably read it, MIT, all sorts of NASA, blah, blah, blah.
All right, thank you. Great. So I'm Wynn Burleson. I'm here talking about ubiquitous reflective environments. And I am from Arizona State University, teaching in two programs, in the Arts Media Engineering program and in the Computer Science program. And so I want to tell you a little bit about that program and the relationships at first, just to get started before we get into the core of the talk. So Arts Media Engineering is a transdisciplinary graduate program, and it has connections with all of these departments. So for example, I'm in computer science and informatics, and so there's a couple faculty that have joint positions in this relationship. I have a student mentored in design, and I work with faculty who are in dance and theater and music and education and psychology. For example, next spring I'm teaching a course on active learning with a professor from School of Education. And this fall, as you'll see late in the talk, a course with the School of Exploration, Earth and Space Exploration, on human-robot interaction on the Moon and Mars. And so there's a very exciting interdisciplinary environment here at ASU, and I have materials I can share with you after. But we're looking to try and think about how media systems affect our everyday lives. And we have four main projects: biofeedback therapy for stroke victims, education projects, interactive arts that are in the proscenium and in everyday life, how to help people be more artistic and more creative. And then we have the education group, which is looking at the education activities. I'm primarily associated with the the communication and everyday activities, sensing everyday life and giving people feedback, as well as the education activities. So you'll see elements of those two agendas in the way that I cover my material. I was at the Media Lab at MIT working with Roz Picard, and one of the attendees here is Ashish Kapoor, and he was one of my classmates at the Media Lab, and we worked together on some of my thesis data and his thesis data, perhaps. What affective computing is a very interdisciplinary agenda that incorporates many of these disciplines. And so what we see here on the left is the social sciences and some of the mechanical and human factors design areas. And on the right, at the top right, some emerging areas of computing in terms of pervasive, ubiquitous computing, wearable computing, and in the middle, some of the core areas of traditional computing in terms of sensors and networks and databases and algorithms. And the areas that are highlighted in blue are the areas that were particularly relevant to my thesis work, which was on an affective learning companion that would help a child understand how to persevere through a frustrating learning experience, to think of learning during that frustration as an opportunity to learn rather than a time to quit. So thinking how to apply Carol Dweck's understanding that the brain is like a muscle, and if you exercise your muscle, you can increase your intelligence. That is a core idea behind the learning companion. And so affective computing, as broad as it is, has the opportunity to bring together some of the social side and some of the technical side, and in so doing, to make some of the major advances that we've seen in other fields when we see disciplines combine, such as in physics and chemistry, to improve our understanding of biology. So today what I'd like to share with you is my work on the affective learning companions, and then how I'm using that work to move forward into ubiquitous design environments that will help design engineers and creative teams work together and better understand their process and their creativity, and in fact support their process. And then I'll share with you the situated multimedia systems part of arts media engineering, that part that is looking at the everyday activity and how to combine understanding of that with recommendation systems and applications that support people's creativity, well-being, and productivity. So let me start off with the affective learning companion. So Flavel had the idea that metacognition had three parts, that it had meta-knowledge, meta-skill, and meta-experience. And so from a meta-knowledge standpoint, Carol Dweck points to a very important message, that there are individuals that believe that they cannot increase their intelligence. And in fact, 40% of individuals will, when filling out her pretest surveys, indicate that they don't think that they have much ability to do well on tasks, that they would rather find things that they could do well at than continue to do things that they're not good at, and that these she calls trait beliefs. That you are what you are and that you can't really improve yourself, but that your general task in life is to find things that you are good at and excel at those. Whereas another 40% of the respondents will find incremental beliefs, where they believe that they can increase their intelligence, and through hard work they can take mastery orientations to material, so they can master that topic. They're not goal-oriented, but they really want to understand the whole process. They may be goal-oriented at a meta level, but at the given time they don't just need to perform well or not. And as you understand when it's important to, say, be mastery-oriented or goal-oriented, this can help you. During learning activities, it's better to have incremental beliefs and be mastery-oriented. And then at the time of performance, it's important, of course, to be goal-oriented. So her message that she's given to individuals is that your brain is like a muscle, and that it grows stronger when challenged. And she has shown that if you can convincingly give this message to individuals, that it can help people in their learning activities. And so what I strove to do was to understand when would be a good time to give that. And looking at flow experience, this is the optimal experience when things are going well. So I wanted to understand when are things going well and when are they not going well. And Mihai Csikszentmihalyi has the theory of flow. And take for a moment for yourself to think of a great time when things were going really well for you. You have that in your mind, whether it be on a sporting field or whether you're having an invention or brainstorming session. Mihai Csikszentmihalyi would say that these are times that are all-encompassing. You're completely engrossed in that activity, that there's a feeling of being in control, and that you have a high concentration and focused attention, a mental enjoyment, and there's a distortion in sense of time. You have all the time that you need, or say in a sporting event, everything slows down and you are fast enough to move around the defenders and shoot the goal. So you are in control. There is in fact a match between your challenge at hand to score the goal, to solve the problem, and the skill in the room. And so this is the match that creates that positive experience. And this is a wonderful time. And this would not be when we would want to intervene. In fact, if we intervene this is a very special moment that is susceptible to intervention and destruction, in fact. And so if you have interruptions during this time, they can be particularly costly. And so to the flow experience and to that optimal experience. So I developed a theory of stuck, or non-optimal experience, that's directly related to this, and is particularly germane to the learning environment. And so it's equally all-encompassing. You are stuck. There's no getting out of this situation. There's a feeling of being out of control rather than in control, and a lack of concentration and an inability to maintain focus attention. There's a mental fatigue and distress even with thinking of the activity. So this is where procrastination sets in, and that long period that we've all had is there's that one or two things that are sitting there that we just can't face, whether they be short-term or long-term. We understand what this feels like. And in fact, Mary Zorinsky and Webro have shown that the distortion of sense of time is productive that as a measure of frustration. And so, for example, people will overestimate the amount of time that they experience frustration. So even though you may only be doing something that's frustrating for 5 minutes, you may feel that it takes 10, 15, 20 minutes long, in direct contrast to the experience of flow, where you had all the time. And whether something took 5 hours, you still were fully engaged. It felt like 1 hour. You can't believe that it's already 8 o'clock and time to wrap things up, or midnight, or 1 a.m., or whenever you wrap things up. One of the most important things, and it gets back to Carol Dweck's message of the brain as being like a muscle and being able to shift your thinking, is that in stuck, there is a perceived mismatch between the skill and the challenge. And it's that perception where there's an opportunity to change an individual's approach. And so if we can say to the trait individualists, you may think that you're not good at this task, And you may not be good at the task, but if you think of this as a chance to learn, you may improve your engagement in the task. And in fact, you may find that you are good at the task, or that at least this perception has allowed you to continue learning about how you learn and how you learn about your affective experience. So as you would expect, this area, stuck, is very associated with negative affect. And one thing to note about negative affect is that it's asymmetric. So it persists much longer than positive affect experience. So a mild positive affect inducement versus a mild negative affect inducement, you'll have lingering effects of the negative affect for a longer period of time. And so in learning, where you're frequently challenged to fail and try again, and in fact that can be a beneficial pedagogy. In fact, it's part of the fundamental pedagogy of constructionism in terms of being able to debug and iterate. All of this experience can be quite frustrating, and there's the opportunity to use intelligent tutoring systems to support people who are stuck and improve their engagement. So what I developed as part of my thesis was an affective learning companion that would create an interaction with individuals that would be supportive and emotionally aware of their activity. So in order to be emotionally intelligent, an affective agent must, one, understand and be able to sense the affective state of an individual, and two, be able to respond with its own expressions, and three, to be able to do those in an appropriate coordination, to be able to link those two, the detection and the response, appropriately. So in a state of stuck, we should be able to respond with direct message, for example. And that is what the core of this experiment was. So this experiment used an agent that was developed in collaboration with Ken Perlin, and the agent was real-time scriptable. It could express head nods, mouth fidgets, and other behavioral characteristics in real time. And here you see the overall context. We had offline video coding to look back at the information. We had a facial expression camera, the Blue Eyes system that Ashish Kapoor was highly involved in. This also came from IBM research as a code base. And had a pressure mouse sensor, a skin conductance sensor, and a posture chair. And these were sensors that were, had been previously used in various experiments in the affective computing group and were generally tuned to learning environments and detection of frustration. And so that's why they were used in this study, brought together. So the rest of the system consisted of a system server that logged the data, an offline inference engine to look at the detection of frustration, a behavior engine to drive the character behaviors, and the output through the character system. So let me share with you now some video of how the correspondence in terms of the social mirroring that this agent could engage in. So you have the participant, you have the sensors, the chair, the mouse and skin conductance, and here you have the facial expression that's mapped up here. You have an ability to interact with the character by speaking. The character can speak, and you can click on buttons. So the first one that's highlighted is under these swaths of color, there's force-sensitive resistors that are capturing the amount of pressure that goes into the mouse. And this is the real-time depiction of that pressure. And the way that that is mapped into the character is through agitation. And so the character sways to a greater extent when the mouse is being squeezed for a longer period of time. All of these are mirrored at a 4-second delay, and they have different thresholds that are set up for the different behaviors. So the character actually has a chance to understand when to create the interaction. You saw the skin conductance sensor, and it's a measure of arousal. So it's a real-time level of the micro sweat on the palm that is not valenced. It could be positive or negative, and the mapping is to the pigment of the character. And so this is either pale or increasingly red. And here we have the chair sensor. As you lean forward or back, you see the posture states here, the pressure zones below on the left, and behind. You're leaning back, leaning forward, and then the overall activity. And it turns out the overall activity and the pattern of that activity is one of the significant elements of engagement. Here, you see the back posture and now the forward posture that can mirror the leaning back and forward posture of the character. And this is the Blue Eyes system. There's a box around the mouth looking at mouth fidgets, blinks, and the eye detection. It's based on detecting the retroreflection of the pupils and then using that to look at the behavioral characteristics. And the character can choose to mirror in the head nod, head shake, mirroring, as well as the mouth fidget, and then finally the smile. So here you see the ability of the system to create the nonverbal mirroring, and then there were additionally the ability to create affective and task-based interventions, and I'll discuss those in a moment. So here is the output for an individual over about 25 minutes. They engaged in 3 activities here at the top. You see they didn't move around in the seat very much. The skin conductance went up and down based on where they were in the activity, and they got pretty excited at the end of the activities. This is the pressure mouse, and then all of this data is data from the blue eyes. And so by looking at information across these channels, Ashish Kapoor was able, and with myself and with Roz Picard, able to detect the frustration detection in this environment when they were willing to click the frustration button at the top versus these other 2 buttons could be predicted at 79% accuracy. And we have that presented now in a forthcoming International Journal of Human-Computer Studies. And so that one is going to be available. And the task, as you can tell, is the Towers of Hanoi. We presented it with 7 disks. We chose this task so that we could calibrate the frustration to our users. So 11 to 13-year-olds were too good at this task. They were finishing the 5 and 6 task occasionally. And what we really wanted was a very frustrating task, so we gave them 7 disks. And that generally caused quite a bit of frustration. What we found was that we were trying to provide affective support and task-based support. So affective support would ask an individual, all the conditions would ask an individual how frustrated, it would say, we know some people can get frustrated with this task. How frustrated are you at this time? And if you said, oh, I'm highly frustrated, or you chose that, or I'm not frustrated at all, the affective condition would tailor its response and would say, oh, gee, I'm sorry to hear that. It must be really hard to be so frustrated. Can you think of, can you remember the message that the mind is like a muscle, and that even though it's really frustrating right now, can you continue with this activity? Do you think you can use those strategies to keep learning? And you'd answer whether you thought you could, and it would go on. So we tried to create a symmetry between that as being an affective intervention versus a task-based intervention that wouldn't respond to your answer. It wouldn't say, oh, it's must be really frustrating. Instead, it would say, oh, well, I know some people like to move the big disks out of the way and then put the small disks where they want to go. So even if you had said, I'm really frustrated, it would ignore that, as most intelligent tutoring systems might, and it would respond with a task-based intervention. It would say other people want to move the small disks out of the way, and then they can put the big disk where they want to put them, and do you think you can use these strategies? Are you willing to continue? So we had this symmetrical in length and opposing approach where, to give you some background, Mark Lepper has shown that affect is part of, in his studies of expert tutors, affect is 50% of the interaction that an expert tutor has with a student. And so having an experiment of this nature to start to show what benefit in an intelligent tutoring system affective interventions might have, that was part of the motivation behind this experiment. And what we found, what we did not hypothesize, was that there would be a significant gender difference. And in fact there was. So the primary hypotheses of the benefits of both the mirroring and of the affective intervention did not bear out, except in when we separated the group by gender. And so when we did so, we found that girls were highly supported in their understanding of their own frustration and their ability to respond with affective strategies when they were receiving the affective intervention, and that this had benefits for them in terms of their meta-affective skill and in terms of their experience of flow. So flow and stuck was one measure that we used, so either less less stuck or more flow. And so these, as you see, were highly correlated, and what this argues is that the affect, at least for the girls, was an important intervention. Boys, on the other hand, tended to be supported by the task support. And here again, for girls, what we find, if we look closer at this issue, is that if we don't have the mirroring, while they're supported by the affect they also are significantly more frustrated. This is the measure of frustration. And so without the mirroring behavior, they're highly frustrated, even though they're getting the benefits of the affect. So they're getting increased awareness of their affective state and how to use those strategies, but they are also being encumbering more frustration. Not until do we add the mirroring do they lower this level of frustration. And so what this argues is that it's important to couple the mirroring with the strategy that's presented. And so boys had had a similar ability to detect the disconnect that a character might have if they don't both have the affective presentation and the sensor-based affective presentation. So that was the primary finding for that, and I look forward to any questions that you have based on that line of work. At this point, I'd like to move on to how I will be using these technologies that sense affect and how I'm applying them to new environments at Arizona State University in the arts community. Yes, your questions. Do you want to? Maybe I should stop for questions on affect.
Oh, actually, I think the mics are like super sensitive today, so
lower
you don't have to talk.
Okay, all right. We can do that at a meta level in the back as well.
Okay.
Okay, great.
I just wanted to add, you said something about affect being 50% of tutoring.
About the strategies of expert tutors, and that was Mark Lepper at Stanford University.
Okay.
So he studied several expert tutors interacting with several students, and that's how he generated those findings. And he tabulated the amount of various activities that they engaged in with their students.
So the feedback you were giving in variations was the mirroring of their...
Right, and the mirroring was compared to a pre-recorded interactive state, so the mirroring of another participant or an average participant that had been taken from pilot studies. So we looked at all the pilot study data and selected the standard amount of motion that occurred and gave them live, pre-recorded examples of previously live information. And so that was the control. We did that also with 5 different samples of that, median samples that were close to the average. And by doing that, so it was that, and then it was also the task versus affect at a single point in time at the mean time of frustration in the pilot study information.
No, so I'm not getting that. So
Okay.
What was the other thing that you gave them?
So we had the character intervene at a given point. The character set up the problem as being, yes.
Okay.
The character introduced the task and then said, I don't really know how to do this, but they told me the rules, right? And so he'd tell the rules and say, I'll watch and help if I can. And so after about 3 minutes, the character would intervene at the mean time of quitting during the pilot study. So that's how we determined how long it should take. And so after 3 minutes of activity, the character would intervene, and it would give either the affective intervention that reminded them of the
muscle.
Of the muscle.
And is that paired with the mirroring, or is that?
So it was a 2x2. So
Okay.
right. So it was paired or not paired with the mirroring.
And then muscle was paired or not paired with the task. Yeah?
Correct. Yep.
Okay.
Yep.
Thank you.
Sure. Sorry about that. Yep. So now I want to introduce the opportunity to create ubiquitous design environments. And I want to start off with some design mantras and just as examples of some of the significant expertise that exists in the design world that could be brought to bear on design and design processes. So Alan Kay has the mantra that the best way to predict the future is to invent it, and Alan Kay is famous for inventing the Dynabook and several other educational technologies. Dynabook was an early prototype of the laptop that had a supercomputer in the room next door, but basically you could start to open the laptop and understand back in the 60s, transition between 60s and 70s, what the laptop might be and become. And so now we have for better or worse, the $100 laptop going out to the world, and hopefully we can make it for better. And I think that there's some very exciting opportunities to do so. So, he invented the future in some significant sense by building it. Kennedy said, we choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. And in fact, Alan Kay also supports this for learning challenges. In his Scientific American paper, he suggests that children and educators should seek out significant challenges that provide the kinds of challenges Dweck finds are good for incremental learners, to teach people to become incremental learners and then provide them the challenges. In fact, Dweck suggests that if somebody solves a problem too easily, you should apologize for giving them too easy a problem and say, oh, that didn't, you know, and that will actually be more motivational and help them continue in their education. So we should, as designers, as educators and learners, seek out really challenging problems. At Stanford, in the product design program, the mantra is that a spectacular failure is better than a marginal success. And by this, the underlying idea is that if you're just striving to be mediocre, you're never really going to get those exciting breakthroughs that you might have if you really go for exciting, spectacular activity. Potentially, those might fail, but at the same time, you've really pushed the boundaries and learned something. And a way to do this is to express, test, cycle. So you express your idea, you test the idea, and you cycle that process until you get it to no longer fail. But in the process, there's a lot of failure, and a lot of frustration, and a lot of stuck. And so other mantras include that the solution exists in the room. This was Land, the inventor of Polaroid. That to use any and all internal and external resources. This is a very actualizing mantra. Wildfogel teaches peak performance psychology at Stanford. And Gandhi said, be the change you wish to see. And so there must have been many understandings to be the change you wish to see. But in a design context, I find that to be quite liberating in the sense that you can do anything in the design context and start to live the experience that, what if we had the laptop? If you want to see the laptop that Alan Kay wants to invent, be the person that's going to invent that and experience it. So live the future, live the present, and experience these changes. So all of these, along with a lot of theory and science behind the design process, has the opportunity, similar to Dweck's messages and Balancen's message about mirroring and agents, and Lepper's messages about the support for individuals, all of the design engineering can also be put into environments that support designers. And so the way I'm approaching this activity is to create a design observatory similar to the activities that are done at Stanford in terms of, and University of Washington, in terms of the detection of the design process and the capture, trying to look at the behaviors that are ongoing in that activity and how to couple them with fabrication facilities similar to those that are being developed by the MIT Media Lab and Neil Gershenfeld. So Neil has 20, 21, 25 of these labs being built around the world, and he's linking them up. They have, you'll see more about that. But if we can put mentors, whether they be avatars or whether they be everyday tools, such as a pen that knows if you're drawing or sketching or brainstorming, if we can try and embed in those systems, in the observatory, in the Fab Lab, and in support, a support for the design process, I believe that we'll do what von Himpel argues, which is to democratize innovation to a much greater extent than it currently is. And so here I'd like to share with you some of the background of Neil's work at the Media Lab. These are some of the elements of the fabrication lab, some of the basic tools that can be put together. On the low end, it's about a $5,000 proposition. On the high end, it's maybe $20,000 for a basic fabrication lab. This could be used in a small city or town in a developing countries such as Ghana, where they are using this type of technology, and they're linking up to the Media Lab and to partners around the US and Europe. And here's a facility, a fabrication facility in action. It's got a number of the different tools that allow you to do rapid prototyping, physical and digital work, and to integrate those. And one of the things we've done this semester at ASU is to use a similar facility to work with Design That Matters on an infant incubator system using the Arduino platform. And this is an open source platform that's relatively low cost and is starting to allow for thermal control in an infant incubator in Nepal. As you see, there's a very significant need for this task, and there's many significant problems in the world that can be addressed by undertaking this process. So what I want to understand is how to better understand this process and how to support it. And so I've been doing some experiments with design engineers in a program it's a capstone program in industrial design called Innovation Space, and it brings together people that are engineers, industrial designers, from business and from communications, and it puts these people in a room together and starts to look at their process. So we've set up 4 cameras to capture the environment. So this is essentially the observatory, the first stage of the observatory. And then we've started to code their behaviors. We've been using Cynthia Atman's process of a playground environment for the first studies, but then we'd like to move on to some of the distributed work such as infant incubator development and other exciting challenges. So here you see the amounts of different activities, whether requests for budget or statements. This work is very preliminary. These are just 3 teams and the amount of the requests for different information. So we're looking for the requests in this case. The more significant interest in the long term is to code both individuals, similar to the work that Cynthia Atman has done, and then to aggregate that information into the teamwork. And so we're working with partners Mark Henderson and Shania at ASU, and looking at how those can be used to understand team process. Essentially, what we are looking for, in a similar way to the stuck flow theory, is when can we provide reflective opportunities in this team process. So when would it be important to tell a team that one of your members isn't particularly participating and maybe give that member some opportunity? So Joni Morrison has shown a opportunity where if you present the barcode participation level of how much any given person has talked, the people that have low barcode levels will tend to talk more when you give them that information. They'll realize that they're not at the average and that they need to step up their conversation. And so instead of being so intrusive as a barcode and so public, you might have a simple avatar that would realize this and say, hey, Johnny, you haven't said very much yet. Or maybe not even say that. Hey, Johnny, do you have any thoughts? So you could use that same information. Or maybe just Johnny's pen starts to vibrate and he knows that maybe in the next 10 minutes it would be good if he started saying something. It would just be one more impetus to start to get involved. And so these are the kind of opportunities, both in the physical activity with the merging of the sketching and the fabrication, and then also in distributed environments, that the kinds of applications that the affective learning companion can attend to. Just one more way that we're analyzing this is the amount of participation by individual and by activity. So that work is all moving forward. Here is yet another way to look at, I said these were transdisciplinary teams. So these are, this would be an industrial design student, this would be a business student. And as you see, this is the amount of behavior in the different categories that they engaged in. So you can tell that there's significant differences in terms of how they engage in different activities. And over time, as we study more and more teams, we want to better understand what are the roles that different people are taking in the team and how do these roles contribute to the team, and where can a technology fill in some of the roles that the team may not actually be taking in on their own. Eventually, I mentioned pens a couple times. We can put environments, parts of the ubiquitous environment, out into everyday life. We can put that in terms of smart badges, such as Sandy Pentland's badge that looks at the way from the Media Lab where individuals are talking and he can determine who is an alpha, beta, or Charlie member of a group. That might be interesting in the design process. Eventually, we can look at end-of-day surveys in terms of the amount of creativity and productivity that occurred today and the affective levels of the individuals throughout the day and link those up. So how much of the understanding of creativity can occur from the technology versus from the everyday survey, and then from the post hoc consensual assessment of the outcomes of the teams. So how creative is the actual product that the team is engaged in. So as you see, there's this wonderful opportunity to mix some of the soft science and hard science of affective computing and to apply it to these really new environments. Let me share with you now the few forward-looking projects that are ongoing in the Art Media Engineering program and Computer Science program at ASU. And so then one of them is the small lab. And so this is an environment. You see some trusses here And it's a 15 by 15 by 15 foot space that has cameras and a projection on a floor. And so individuals can be in this space, up to 15, 20 individuals in this space, moving around with objects. We're setting up an RFID tracking system so we can know where each individual is and what they've been engaging in to the extent that they've moved their body in the space. So far we've been teaching dance and movement. What we're moving into now is STEM, science, technology, engineering, and math topics, and how to do gravity with the ball or spring constant. So you're moving the ball and you're getting a virtual spring to move around. You can change the spring constant with the spring. You raise the ball or lower the ball and you get different levels of gravity. So you can start to explore in an embodied sense the type of educational opportunity. One of the exciting things that we're looking forward to is how to use robotics and robotics education to embody the robot and try and take care of some of the shared world activities of the robot. So one of the big challenges in human-robot interaction is that it's difficult for humans to share the world perspective of a robot. And so in this environment, we'll be testing what does it mean to give somebody that shared world experience, and then does that allow the individuals to experience a greater bond with the robot, either as a tool or as a peer. So that's moving forward. We also have an environment at ASU that's really exciting, that needs more use, and we're planning to do a lot more use with it. We're moving the small lab into the decision theater, which is a 270-degree back projected environment that supports about 20 individuals in the space and is based around decision making. So the class that we're teaching in the fall is a exploration of the moon and Mars, and running a simulation between an astronaut, a rover, and a mission, and looking at how to project virtual environments, whether it be water or mineral resources, into that space. So here's a higher resolution. We'll have I create robots, and we're starting collaborations with Honeywell to look at whether at some of their work on robotics and lunar missions. And looking at the way the course will run is that we're going to run the mission iteratively in that express test cycle method. So the first day we're going to have a flip chart where everybody in the class has a role and participates in a mission, either on the mission control team, on the astronaut team, or on the rover team. Or perhaps in the scientific, what are the objectives and what are the resources to understand the scientific objective? Or finally, what is the cost to the mission to change the position of anybody or the cognitive load of anybody? So looking at a really significant part of how do you share the information across all of these channels. And so every 5 class sessions we'll run the mission again, and the students will become better and better at understanding what are the issues and improving the technologies that they have to deal with the mission. And by the mission 9 and 10, we'll have the final, and we'll project a new crater in that environment, and we'll see how effective their strategies have become. And finally, at Art Media Engineering, we are looking at the everyday public space. So one of the recent activities out of my physical computing class was to understand how do people behave in a public artistic space with interactive installations. And so we used the design observatory cameras to capture the interactions with the installations, and we used the installations to record the sensor level data that each of the installations engaged in. And so now we're looking at a similar process to code that data to understand the experience relative to the surveys that we took from that experience of the users in that space. So we hope that that will have some interesting implications for the way artistic and interactive installations get installed into public spaces. Here's another picture of the types of public spaces that we have in Phoenix. And one of the interesting things about this project is to understand the challenges in a desert climate in terms of the dust and the sun. So traditional uses of screens may not be the most appropriate. We might have to go to more sound systems or new ways of using screens that use the sunlight rather than fight the sunlight. So with that, I'd like to close and open the floor for any questions.
Can you say a little bit more about the mission robot?
Yes.
Thing? So will when they come in, what exactly is the mission they're going to do, and how will that change?
Yeah. So we have set up the class as having a science team that would try and understand the opportunities of the mission in terms of what are the mineral resources, what are the objectives in terms of water or helium-3 that might be opportunities, or in terms of fundamental planetary geology. The context will be a crater that will be projected in that environment, and then they can move around within the room and explore the crater. They can do that both as a science team prior to the mission, but then with whatever low-resolution data might be available to us today. But then during a mission, they would have the high-resolution experience where they're actually moving around that space. In that space, since we'll have a couple outcroppings, so we'll have some rocks in the room that astronauts and rovers will be working on, and they'll move to those spaces. We'll also have the mission control team and the mission information in terms of what are the priorities, what are the safety levels or the power levels on the robot, or the energy levels or the load levels of the astronaut. So each of the three teams, the astronaut, mission, and rover, will be focusing on the communication on each of those lines. So we've put the team across mission astronaut or mission rover or rover astronaut. So those will be three teams. The other two teams, one the science team, and then the other is a combined energetics, physiology, and cognetics team. So looking at how much cognitive load is in any given place, how much energy does it take to move anywhere, and how much biological resource do we have in terms of fatigue or sustenance or safety from the astronaut. So the team will between the missions, they will be working as individuals and teams or individual teams to try and figure out what they can contribute to the overall mission. And then during the missions, they will work together across those teams to fulfill the missions. And so their mission, the first time, it's a flip book. We've designed a mission for them. They will start to understand what their teams and individual roles are. And then from there, the rest of the class is open-ended ideation and exploration express test cycle, where they will be learning the process of the scientific method and the design method in collaboration with each other and with the instructors, myself and the head of the School of Earth and Space Exploration. And then we will also be looking at how to use the decision theater as a new model for education across the university. So in the fall, we'll be teaching this class. In the spring, we'll be teaching a class on complex ecological systems and how at the graduate level. And so between these two classes, by the end of the year, we should have a very interesting set of information to explore how and if ASU should be building more of these and teaching more classes in them, and what kinds of classes are afforded by this opportunity. Yes?
So I'm really interested in the first study you did and
yes.
how you can help users maintain flow and make a transition from a working environment, goal-oriented, to a learning environment, sort of just in time back to that working environment. Do you have any thoughts on that and how?
Well, tell me a little more about one or two of the thoughts that you might have about that, and then I can try and contextualize. So what would you see as a possible application?
Today's information workers and how it can be frustrating to work with software and how to make that a better experience. And I'm wondering how these principles might apply.
Well, we've been talking about that this morning with some of the different studies. I was talking about logging all the frustration that somebody has in a given day with all the different technologies, ranging from simply getting into an elevator that won't let you press a button up because it thinks it's going down. You get out, it closes the door and it opens again, and you go back in and now you can press up. So that's a small little example. One of the out there possibly options is a meditative experience in terms of having things wash over you and not think about them, not internalize them. One of the interesting things from the studies of the pressure mouse was looking at the level of frustration as an implication for the ergonomics more than the overall usage. So that was the study that Dennerlein and Picard did with their pressure mouse. So there are a lot of opportunities to help people better understand their frustration. Understanding their frustration alone can help to mitigate that. And so part of the overall approach to affective computing is to to start to create opportunities for this. So one of the specific ones we were talking about this morning was the study of RSI and ergonomics, and so how to provide opportunities for stress relief. And that might range from the 5 to 10 minute, 30-second breaks, but it might also be important to take those longer 5 to 10 minute breaks that might be a very meditative experience that might sort of reset the overall threshold. So the small breaks might just be working at the fluctuations, where the larger breaks might be resetting the current threshold. And so starting to look at those and looking, say, at the SMART badges, for example, Teresa Amabile showed that overall time pressure impacts creativity, but in the opposite way that people think that it does. People think that creativity is improved by time pressure, and in fact, in general, it's degraded by 45%. And so helping people better understand this relationship and the amount of time pressure they might be under, and whether they should be engaging in creative tasks or algorithmic tasks, might be an opportunity to start to deploy some of these activities.
And specifically, when a user has to transition from a goal environment to a learning environment, does it help, in your experience, to make them aware of that and to make it an explicit thing, or try and be more seamless?
Right. Well, I guess I would say that the work environment doesn't necessarily always have to be a goal environment, that there should be a combination of a significant amount of learning in the work experience as well, right? And so I wouldn't necessarily make the transition as explicit as moving from a goal environment to a learning environment in that sense. I would try and incorporate, right. And so I would incorporate those. I think there's a lot of opportunities in terms of, say, persuasive technologies or peer support or computer-supported collaborative work to draw in different people. Like I was talking about creating models of mentors. Some of those models can be embedded. Others actually bring in mentors at given times. I think that can be applied to the workplace when needed. So supporting extreme programming for a given period of time, and then saying, hey, it might be time to, you've been banging your head on this problem as a team, even as a 4-person team for a little while. Maybe it's time to step it up a little and get a more experienced person in here just for a few minutes or for a longer period of time. The systems might have the opportunity to start to detect some of that based on some of the behaviors. Certainly ITS systems, intelligent tutoring systems, have started to look at gaming the system or incorporating models of the user's knowledge in understanding how to support them. So I think extreme programming environments that were sensitive to what kinds of strategies people are using to solve their problems could start to see, hey, certain people have certain patterns, and it might be productive to teach them, give them a mini course in a new pattern that might be a complement to their old pattern. I guess a very explicit one that I'm excited about is some of the thinking on creativity as being incrementalists, being adapters, and innovators. And these being two strategies of creativity that aren't better or worse than the other, but some people take an existing solution and tweak it a little, and it's highly creative now. Others take that existing solution and they jump way over here. And it may not be better or worse than the adapted one, but both are seen as being creative. And so it's thought that these are part of individuals' approaches to creativity. And, for example, tools that would either put two individuals together that could work together across those with different backgrounds, or tools that would support an individual who might be adaptive to be innovative, or an individual who is innovative to engage in, hey, don't be so innovative for a little, what could you do just right around here? Could allow both of those individuals to help in the overall creativity and productivity of their work process. So I think there's a lot of opportunity to understand what the research and literature is saying and apply it in experimental context to see to what extent can the technology actually make the improvements that may be possible.
Okay, thanks.
Okay, thank you.
Well, thank you.